Hi there and welcome to the screencast for Lab 4, the final lab this semester. Right, so we're going to be looking at data on kidney stone treatment. So we have almost 8,000 patients treated for kidney stones using one of two treatments. So we've got two treatments, A and B, and we have whether the treatment was successful or unsuccessful. And so that's going to be the main outcome variable, successful or unsuccessful, and we've also got the size of the kidney stone, whether it was small, medium or large. So the data are all categorical. Let's read it in. And so because it's categorical, essentially what we're going to be doing is comparing the proportion of success, right, across the different groups. So you can see when we read the data in that we have the three variables, size, treatment and outcome, and you can see that around about 80% successful of all treatments in all patients, and about 20% unsuccessful. The treatments are relatively balanced and the size is relatively balanced as well. Across the different groups, there's a similar number of each size stone. So we're going to start with a plot of treatment by outcome. Okay, so we've got just a standard stacked bar chart here, and because the number of observations in each treatment group A and B are about the same, right, we can see that here, there's only two different. The normal stacked bar chart is essentially equivalent to a filled bar chart where we have proportions. So we can estimate the proportions here really well because the height of the bars are the same, the total height of the bars are the same. So what we see is that the B tends to be more successful than A. Right, so, but not by a huge amount. Okay, so let's just write that here. Treatment B seems to be more successful than treatment A overall. The difference isn't all that large. Okay, so instead of graphing it, we could use a table. So the table command can be used for this. And we're going to save the table here, okay, into a variable called tab, and then look at it just by typing the name of it, right? So if we run that first line, we're going to get tab, right? So there it is there. So it's a table of size 2 by 2, and we can spit it out. So there it is there. Okay, so you can see here that there's just from this table here, you can see that there's more unsuccessful in A compared to B, and there's more successful in B compared to A. So that gives us a good feel that B is maybe better. But it's hard to see because these aren't proportions, right? You can't directly compare the proportions here. You'd have to work out the totals yourself, which is easy enough, and you're welcome to do it by hand or with a calculator. We can, of course, we've got a calculator on our desk. This computer is a calculator. So we could use a prop.table command to work out the proportions for us. And the prop.table command basically takes our existing table tab, which is this one here, and it just divides each number by either the row total or the column total. So in this case, we're wanting to divide by the row total in order to get the proportion successful for A and the proportion successful to B. So we use margin equals 1. Margin equals 2 would do the same thing, but would work out the proportions out of the column. So it would give you, of the successful ones, what proportion of them had treatment A, of the unsuccessful ones, what proportion had treatment A or B. Okay. So here's our proportions table. So you can see that across the rows they add to 1, and you can now compare these two numbers, and you can see that B is a little bit better than A, but there's not a huge difference here, is there? And because there's not a huge difference, we think that because we only have a sample, admittedly it's quite a large sample, we have 8,000 individuals essentially, so we have quite a large sample, so we might expect to be able to detect quite small differences and be able to infer from our large sample that that there's differences in the population. And we can do this, of course, with a hypothesis test. Now that we don't actually need that line there, because that's just repeating this line here, the table command, because that's just repeating the line we've already run up there, isn't it? So let's get rid of that. That's a mistake by me. So let's run prop.test. So just like when we're testing means, we use t.test. Okay, we saw that for testing whether there was a difference between right and left wing length between petrels. So right wing length between petrels of different sexes. Prop.test does the same thing but tests proportions. Okay, so you run it on a table and it works out whether there's a difference in the proportions for you. Okay, so you can see here it's given us the proportions in each group. So you can see here that proportion 1 here must be A, right? It's the first row in our table. So it's the same number there, and proportion 2 is for B. So you can see in our sample we had a difference, right? And so what we want to know when we do the hypothesis test is whether that might hold in the population as well, right? So remember, when we do hypothesis tests, is what we do is we make a claim of no difference in the population. So let's assume that treatment A and treatment B are equally successful in the population. Then when we take a sample of individuals and apply treatment A and B, then we might get a slight difference in the success rates between A and B, just due to random sample-to-sample variation, just due to the individuals that we happen to choose from the population. Okay, and sometimes we'd get a difference. So if the difference in the population is 0, then we'd expect the difference in our sample to be close to 0, but perhaps sometimes treatment A might do better, and other times treatment B might do better. So what we want to know is how often would treatment B do better, like we saw in our sample, by the amount that we saw in our sample. So you can see here that the difference between these two is about 2.2%. So this is 79.5%. This is 81.7%. The difference between those is about 2.2%. So how often would we get a difference as large as 2.2% in a sample if in fact there was no difference in the population? That's what the p-value is telling us. So it says the probability of getting a sample where the difference is at least 2.2 is about 1.4%. So that's quite low, isn't it? Right? So we must have got quite lucky to have obtained this particular sample if in fact the treatments were the same. The alternative, of course, is that the treatments are not the same and we haven't got lucky, we're just observing the truth. Okay, so because the p-value is quite small, our conclusion would be that we have evidence against the treatments being the same, right? Because we just don't believe that we got that lucky. So let's write down something about that. So the hypothesis being tested is that the two treatments are equally successful for the population of all people with kidney stones, right? We didn't see this in our sample. In our sample, treatment B was better than treatment A by about 2.2%, right? So that's just difference between 79.5% and 81.7%. The p-value tells us how often we'd expect to see a difference in the samples, in the treatments, as large as this, given these, as large as this in a random sample, given there's no difference in the population. As the p-value is small, we must have got quite lucky to observe this particular sample. So let's write down what it is. So instead of just saying it's small, we can actually just note down exactly how small, so that in case we make a decision that someone else disagrees with, they have some information in order to go with that. Alternatively, more likely perhaps, we just are observing a true difference and our hypothesis was incorrect. So the small p-value is providing evidence against the two treatments being equal. So we'd conclude that there's probably a difference in the population. Right, so remember that the p-value is telling you something to do with the population, right? So it's the whole point of statistical inference is to go from what we see in our sample to something in the population. And of course, we saw a specific effect in the sample. We know exactly what it is. We wanted to go back to the population and assess whether what we saw in our sample was likely to also hold in the population. So that's with the hypothesis. What about the confidence interval? So the confidence interval is here, and it should be telling us the same thing. And you recall that your confidence interval is doing things a different way from the p-value. So the p-value does things sort of in this weird backwards way where we assume that the two treatments are the same. We then observe that they're not the same in our sample, and we just say how often would we expect to get a sample that looks like that due to sample variation. And if the p-value is small, so if we say, well, hardly ever, then we'd conclude that it probably didn't just arrive by chance, but instead arose due to some actual differences in the population. The confidence interval does things the other way. The confidence interval says, given what I have in my sample, can we then give a range for the population where that sort of captures the difference that we think there will be in the population. So essentially what we do is we take the observed difference in our sample, so you can see that we can do 0.795 minus 0.817, we'll get 0.022, right? That's that 2.2%. So we get minus 0.022, and then we add some uncertainty around that in order to hopefully capture the truth in the population. So that's what this confidence interval here is. We've taken minus 0.022, which is right smack bang in the middle of this interval, and we've subtracted off the standard deviation of that value and added on the standard deviation of that value and got a range which is 0.04 to 0.004. Okay, so we're 95%. So in our sample, we observed a difference of minus 2.2%. Which is A minus B. We're 95% confident that the difference in treatment success rates, A minus B, in the population is between minus 4% and minus 0.4%. Right, so you remember that this is for the population. So what we've done here is we've taken our observed number, minus 0.22, that's the exact difference we observed in our sample, and we've added some uncertainty to that, and then once we've added that uncertainty, that then gives us a range of potential values for the difference in treatment in the population. So what we're saying is that we're 95% confident that whatever the difference is in the population, it probably lies between minus 4 and minus 0.4%. So because both these numbers are negative, because this range precludes 0, there's a difference in the population with treatment A having a lower success rate than treatment B. Right, because we've done A minus B and it's negative, so A must be less than B. Right, so that's so we've concluded that B is better. B is better than A. Okay, so now we're going to go on and we're going to assess what effect the size of the kidney stone might have on treatment. So we're going to do the same. We're going to start off with the same graph, and now we're going to split this up by the different size. So one way to do that is to add some faceting by the size variable. So you remember you can copy and paste this essentially from lab 3. We did the same thing for the petrels data where we faceted across area. Right? So essentially what we're doing is we're breaking the data up into the different size stones, and then we're plotting the treatment versus outcome for each of the stones, and we get a graph that looks like this. So what we see is that the number of individuals, i.e. the total height of the bars here, is different depending on the size of the stone. So in the medium stones, we're applying treatment A and B equally. In the large stones and the small stones, we're not applying them equally. Okay. The other thing that we can see is that, well, the thing that we're primarily interested in is the difference in outcome, and it's very, very hard to compare the difference in outcome within the large stones here, because it's hard to compare the proportion of blue versus red in these bars, because the total bar length is different. The same here. It's hard to compare these. So we might want to do another plot, which adds in position equals fill. So you remember we're adding position equals fill goes inside the geom bar because we're altering the geometry of the bars. But it goes outside the AES because inside the AES, of course, is only stuff from our data. So we have, essentially, we've got two parameters going into geom bar. We've got mapping, which is given by the AES bit, and then we've got position, which is just given by fill. Okay. So now we've got our two graphs. We've got our one we had before, and we've got a second one where essentially all we've done is converted the counts to proportions. And now we can clearly see that A is better than B in all cases. Note that that's somewhat strange, isn't it? Because back up here, clearly B was better than A overall. But when we look at all the different size stones, in fact, A is better than B. Now that should hopefully be somewhat counterintuitive to you. So we're going to repeat the process of testing to see whether this difference that we see in our sample holds in the population, and then later on we'll see if we can sort of come up with something that explains this discrepancy. So what is our conclusion from these? Is it unexpected? Yes, it is unexpected. We see that treatment A is more successful than treatment B in the large stones and in the medium stones and in the small stones. This is the opposite to what we saw before when we looked across all sized stones together. Weird. Okay. So we want to know whether this this same odd effect that we've seen might also hold in the population by performing a hypothesis test. So we can clearly see that there's a difference in our sample within large stones, medium stones, and small stones because we have that information directly in our sample. What we want to know is whether it holds in the population. So we're going to do the same hypothesis tests. So first of all, what we're going to do is we're going to pull out just the small stones into a separate data set. So that's what this first subset command does. Right? So we can use subset to find a particular observations in the data. Right? And so we're finding the things such that the size is small. So you can see that within this, we've got 2,856 observations of small, which should agree with what we had back at the start. Right? So we can see here that we've got 2,856 small stones. So we just pulled those ones out. And now we're going to repeat the process using the small data set instead of the kidney data set. So essentially what we're going to do is we're going to rerun these lines of code here. So we're going to regenerate our table. We might do a prop.table to get an idea of the proportions. And we're going to do a prop.test to test whether those proportions are different in the population. So we're going to table up things. So there's the there's the table of the small stones, the success rates between A and B. Again, these are hard to compare because, of course, these are proportions. These are counts, and we want proportions. So we're going to add another code block, maybe down here. In fact, what I'll do is I'll just come and steal this one from up here. I'll grab this one here, just so that we can convert things to proportions. Right. And then we might also do the test here in here as well. So what we're going to do is we're going to use our small table here in place of our table. Margin equals 1 to get the row count. So let's have a look at those. Right, so now we can compare them. So we can see that clearly A is better than B. So A is 93% successful, B is 87% successful. So there's a difference of about 6% between the two. Okay, 6.5% maybe between the two. And that's what we see here. Okay, so now we want to see, does this hold in the population? So let's do a prop.test on that small table again. And what we find is, of course, it tells us what the, it gives us the same proportions, right? So proportion 1 is again A and proportion 2 is B. So our conclusion is that, so the hypothesis being tested is that the proportion success in the population between both treatments is the same. For both treatments, perhaps. This wasn't the case in our sample. In our sample, the difference in treatment success rates A minus B was about 6%. This could happen by chance due to sample variation. If the population rates were the same, about 6 and 1 million of the time, right? So I've converted that to I mean, we could just write it as decimal, I guess. So it's 0.000006 of the time. We either got super lucky, or we're seeing, or the hypothesis is not true. So we'd conclude we have quite strong evidence against the proportions being the same in the population. So we'd conclude that they're probably different. Again, from the confidence interval, we're 95% confident that the difference between treatment A and B success rates in the population is somewhere between 4% and 9%. Right, so 4% and 9% with treatment A being better. Okay, so that's for small stones, and we might expect to get the same thing for the medium stones and the large stones. So looking at it, I can see that maybe the effect size within the medium size stones is a bit smaller, so we'd expect our p-value to be a bit bigger, and for the large stones it'll be somewhere between the two, right? So because the effect size here, the actual difference we observe is actually quite small compared to is sort of in between the medium sized stones and the small sized stones. So let's repeat this same process. We'll just copy and paste these chunks, and maybe we'll just put it all into one. Right. So let's do that here. So we're going to grab the medium sized stones. I'm going to call the data set medium, just so that I don't confuse myself. So now I've got the medium, which is 2,394. Then I'll do a table that up. Spit it out. And then we'll also do a prop.table on that to get proportions, and then we'll do a test. Okay, so we'll run all that code. So you can see here's our table. It's actually not too bad to compare directly because the counts here in the columns, in the rows are almost the same, right? So we can easily see that A is more successful than B and B is more unsuccessful than A. Converting to proportions, we see that 83% of A is successful and just under 80% of B, so there's about a difference of just over sort of about 3.4% or so. From the test, we see we get the same estimates as expected. The p-value is small but not super small, so there's some evidence against the hypothesis that they're the same, and the confidence interval says the difference in the population is likely to be between 0.002%, 0.2% and 6.5 or 6.6%. Okay, so let's quickly write that. So hypothesis is that both treatments are the same in the population. The p-value is 0.038, so we got reasonably lucky here. So the difference observed in the sample might be due to chance, but we'd have to have been reasonably lucky. So there's some evidence against the hypothesis. Now this is confirmed with the confidence interval, which suggests that treatment A minus treatment B success rate in the population is somewhere in the interval 0.2% to 6.6%, with A being better than B. So evidence of a difference, but the difference might be quite small. So we don't have as strong evidence here for a difference in the medium stones, but there's something going on, and particularly it's the same direction, right, with A being better than B. So repeating for the large stones. So what about large stones? So we're going to grab large. And we will just redo all of these. So we can see that the large stones again are more, A is more successful, 73% versus 69%. Difference is about just over 4%. Again, our p-value is not super small, 0.04. And there's our estimates there, and there's our confidence interval, right? So again, we have the same hypothesis that has the same success rate in the population for large kidney stones. The p-value is 0.04, so it's providing some evidence, but not a lot, that there's a difference between A and B rates in the population. Success proportions in the population. The confidence interval, so we're 95% confident that the difference in success proportions between A and B lies between 0.09%, so it's quite small, isn't it, and 8.4% in the population. So remember that both of these things, the p-value and the confidence interval, is telling you about the population, right? So this makes sense because, of course, we know what's happening in our sample. We saw a difference in our sample. We know exactly how big the difference was in the sample because we can compute it directly. We don't know that about the population, so that's why we're providing a little bit of sort of adding a bit of vagary around our statement. So we're providing some evidence, but maybe not a lot. So we're, allowing ourselves to be wrong, because if we're concluding that there's a difference, our p-value is only 0.04, so that's telling us that actually we would have observed this difference just due to chance about 4% of the time, right? So that's suggesting to us that it could have been chance, but we've got reasonably lucky here. This is like 1 in 25. Right, so we've got lucky, but not super lucky, right? So this might just be due to chance. There's some evidence, but not lots. Okay. Nonetheless, what we saw is a common trend in that A was always better than B, right? Which is what we saw in our plot. And so this is a little bit strange, isn't it? Because of course, overall, B was better than A. And the key thing that we haven't looked at yet, or we haven't discussed in great detail, is that size is actually what's making the biggest difference here, right? So if we look at our plot here of proportion success rate, what we see is that within the small stones, even if we use the worst treatment, which is treatment B, right, we still have a better success rate than we do with the medium stones where we use the best treatment, treatment A. Right, that level there is less than this level there. So the size of the stone here is making a bigger difference than the difference between the two treatments. Right, so the key thing that contributes to the success of the outcome is the size of the stone. Similarly here, right, so large stones have a much lower success rate than medium stones, which have a lower success rate than small stones do. So the biggest thing driving the outcome is actually the size of the stone, not which treatment you use. Okay. Nonetheless, there is a difference in the treatments within each, regardless of how big the stone is. But the key thing is that they haven't been applied equally, right? So they were applied equally within the medium stones, but they were not applied equally within the small and large stones. So within the small stones, we applied B more often than we applied A. And of course, small stones are easier to treat. In the large stones, we applied A more than B. And large stones are harder to treat. So if you like, what we've done is we've penalised A, treatment A, by applying it more to the large stones, which are hard. And we've given B an easy ride because we've applied treatment B more to the small stones, which are easier to treat. So when we ignore the size of the stone, it seems as though B is doing better simply because it's had more successes. But all of those successes have, of course, come from the easy cases, the small stones, or most of the successes have come from the small stones. A doesn't look as good, and that's because it's had more failures, more unsuccessful results. But all of those unsuccessful, or the majority of those unsuccessful results have come, of course, from the large stones, which are hard because they're large, not because we use treatment A. Okay, so the key thing here is size matters for kidney stones, at least. Okay, so let's write a little bit about that down the bottom. The size of the kidney stones contributes more to the outcome than the treatment type. So for the small stones, it doesn't matter which treatment you use, you'll still get a better outcome than with a medium stone. Similarly, with a large stone, you're going to do worse regardless of which treatment you use. Then, the two treatments have not been applied equally across the size of the stones. Treatment B has been used more often on the easy cases, the small stones, while treatment A has been used more on the hard cases, the large stones. So when we ignore the size of the stone, i.e. when we look across all cases, it seems as though treatment B has more success. But all that success is coming from the easy cases. The key thing to remember is that the relationship we see between outcome and treatment has been confounded by the relationship between by a third variable, size. Size both affects the outcome and also affects which treatment is used. So the relationship we saw between outcome and treatment is completely reversed due to the effect of size. Once we account for that third variable, we see that the relationship between outcome and treatment is completely reversed. So this is an example of what's called Simpson's paradox, where essentially if you look at two variables alone, then you get one conclusion, but when you separate it by subgroups, that within each subgroup you get a different conclusion. And it's happened, and there's many famous examples of this. So one of the ones that I like to use is that there was a study in the 70s done of women in the UK. In a particular town, they went and surveyed a bunch of women, and one of the things they asked them was whether they smoked. They then went back to the same town 20 years later and to sort of follow up on these women, and they found that a certain proportion of those women had died in the preceding 20 years. And when you table up the number of the proportion of women that died within those that smoked and those that didn't smoke, it appears that smoking is protective, i.e. more of the smokers were still alive than the non-smokers. More of the non-smokers died. And that's sort of counterintuitive, right? Our intuition is that smoking is not good for you, so shouldn't help you survive. Smoking, in fact, is more likely to result in death, right? Because it is highly correlated with lung cancer, for example, and throat cancers and things like that. So why does this happen? And so when you look at the same data, but you break it down by age group, so you break it into young women, middle-aged women, and older women, then what you find is that within each of those three subgroups, if you do the same thing, so if you look at the proportion of smokers that died and the proportion of non-smokers that died, you get the exact opposite result, in that within each of those subgroups, smokers were more likely to die than non-smokers, which is what you would expect. So when you ignore the age variable, it looks as though smoking is protective, but when you account for the age variable, you get the correct result that smoking is definitely not protective. In fact, it's a risk factor for death. And of course, the reason for this is that the smoking rates within those three age groups differed, right? So the older age group had a lower rate of smoking than the younger age group. And of course, the older age group were more likely to die, not because they smoked, because they didn't smoke as often, but simply because they were old, right? So the key variable influencing death in that study was how old you were in 1970, because that influenced rather dramatically whether you were still going to be alive in 1990 when they followed you up 20 years later, right? If you were already in your 60s, then you had a much higher chance of not being around in the 20 years later compared to someone that was in their 20s, right? So that's another example where if we ignore the age structure in the data, which highly influences the outcome variable, we're going to get a different conclusion about some other variables. And there were other cases in that same example where it happened. Okay, so it's an example of Simpson's paradox. If you want to Google that, I'll just add this in on the sheet. And I'll give a link to the Wikipedia page maybe, shall we? Let me find that for you. Which has some other examples plus a bunch of maths probably as to how it happens, in case you're interested in that. Right, let's knit that and make sure it all works. There we go.